This example says, find the volume of the solid that's bounded above, well, it doesn't say bounded above, but it says it's bounded by the surface, z equals e to the power negative x squared, and the xy plane within the region R. But e, the exponential function, is always going to be positive, so z is always going to be a positive number anywhere in the xy plane. And so that means it's going to be on the top side of the surface. And the base of the solid is going to be this triangular base that you see here. And so the way I would find this volume is by taking a double integral. And then my integrand is going to be that function e to the negative x squared. And then I would have to integrate this somehow. Say like dx dy. And then how would I describe this region in the plane? I would say, well, y, my y variable, my outside integral, y is allowed to be anywhere between 0 and 1. But x can only be values between y and 1. And then you would say, okay, let me take the antiderivative of e to the negative x squared with respect to x, and you'd say, oh crap, I can't do that, right? You can't find that antiderivative if we do this order of integration. Does that make sense? You know, this is one we've talked about a lot. This is just doesn't have an antiderivative with respect to x in the terms of elementary functions or any kind of combinations of elementary functions. And so what we would do is we would change the order of integration in this case. Since this isn't working out for us, what we can do is instead try another double integral where I take dy dx instead. And now I have to say my x variable is allowed to be anywhere between 0 and 1, but my y variable has to be between 0 and whatever the x value is. You know, because this region is bounded from above by the line y equals x. That little triangular region in my domain.
So the graph of z equals exponential of negative x squared, is it only on the xz plane or is it on the whole?
That's a good question. Yeah. Yeah, so you're saying z equals e to the negative x squared. It's really only a function of one variable, right? And so with respect to y, that function would be constant. And so if I type in z equals e to the power negative x squared, right, the red axis is my x-axis. And so z as a function of just x would look like that, right? Okay, but since it's constant with respect to y, the surface is flat if you only look in the y direction. So that's the surface we get. Does that make sense? Okay, so then I could look at the region, which is this triangular region that would be in there, and say, what's the volume of the solid over that triangle but under the surface? Okay. All right. So it's a good question.
So y is just a free variable?
Yeah. Yeah. So changing the order of my integration.
I didn't get it. Why we have to change the order of integration?
Why?
Yeah.
Okay. So if we tried this first way I wrote it, if you tried to solve this problem, the first thing you would need to do to take the inside integral is to say, I need the antiderivative of that with respect to x. But what's the antiderivative of e to the negative x squared with respect to x? Yeah. So it turns out there's not one. Yeah. You can prove that this integrand, I mean, I can't prove it, but mathematicians have proved it, that this integrand has no antiderivative in terms of elementary functions. So you can't write any combination of polynomials, rational functions, sine, cosine, exponentials, logarithms. There's no combination of functions that describes the antiderivative of e to the negative x squared. Okay? So that means none of the strategies we learned in Calculus 2 are going to work, right? Like you can't do a U sub, and you can't do any sort of trig sub, and you can't do anything to this that's going to find an antiderivative. So if you hit that roadblock, the next thing you can try, since this is a double integral, is you can try switching the order of integration. And so switching the order of integration is going to work in this problem. Yeah. So when we switch the order of integration, now I'm trying to take the antiderivative of e to the negative x squared with respect to y. But with respect to y means that x is a constant. So e to the negative x squared is a constant. And so this antiderivative is just going to be y times e to the negative x squared, evaluated at 0 and x. That's a very easy antiderivative to take. And then evaluating at x and 0 just means I replace that y with an x. And what strategy should I use now to take the antiderivative of x e to the negative x squared? U sub, yeah. So I'll say that u is equal to x squared, which means that du is equal to 2x dx. So I can replace the x dx by 1/2 du. My lower bound of 0 would be 0 squared, so it's still 0. My upper bound of 1 would be 1 squared, so it's actually still 1. And so the antiderivative of e to the negative u would be negative e to the negative u. And I plug in 1 and I plug in 0. So e to the negative 1 power would just be e to the negative 1 power. And then e to the negative 0 power would just be 1. So our answer is going to look something like this.